Okay, before the break, we were kind of talking about numerical representations, something you probably should have seen before in the SDEV 120 class. The numbers we use in daily life in America are based off 10. Nothing special about 10. We can do that same representation with any base, including base 2. And all of our rules of math still hold. Fractional values just kind of go the other way. Whenever we have numbers smaller than 1, we put the little dot, and then on the other side we just have a power of 10 in the bottom of a fraction, so we're getting smaller and smaller things, and then it still goes subsequent powers. We don't need to dive into it that deeply for this class. But using the integer representation, those rules of math we know still apply. We can add and subtract, and we can represent our numbers that way. So we have a pattern, and that's part of that definition that was written up there earlier. So a machine that can detect, identify, and react to a change of state. So now we have a way to identify every one of our states. And this is really what that change of state is. So like this one right here, if this 0 switched to a 1, the computer can detect that change, identify what it is, and react to it. That base level of what's going on there. Gives us a way to match patterns, to do our math. And it's not new. In ancient Egypt, so I'm actually a math person, for those who haven't heard this before. My highest degree is in math, and I'm currently working on higher degrees in pure mathematics, not in technology. I just know a lot about computers. My computer degree is the only degree I have a bunch of degrees, but the only one I have, other than certifications, is for computers, is an associate's from Ivy Tech. This is certifications, and all the higher degrees are in pure mathematics. But when the software development position opened up here, there was more concern about experience than paperwork, because sometimes just the paperwork doesn't work out so nicely. And when they mentioned it, I was like, oh, definitely not being a math teacher. When it was brought up, I was like, oh, programming, that's what I do on the weekends for fun. It's a lot of fun. And after tonight, our lectures are going to be example based. We got to get to the review section real quick. So when I was getting my math degrees, in the history of math class, I had to do math the ways a lot of different cultures throughout history have done them. And ancient Egyptians used binary. So it's not new. Ancient Egyptian scribes did this. They wrote down base 10 because it was easier to write down. But then whenever they needed to actually do math, add and subtract and all of that stuff, they would take the base 10 numbers based off 10 fingers like we use, convert them into binary numbers, and then all our math becomes a yes/no question. They would do the math with that simple yes/no, the simple yes/no questions, and then convert the result back to base 10. So this is not anything new at all. This is what we just went over, is how ancient Egyptians did their math. Can I erase this section for the next little bit of review? That's from before the break, so hopefully it's in everybody's notes that was taking notes. And after tonight, the rest of this class is pretty much going to be all examples, and we're doing code and stuff. We can talk about this stuff first. So 2 things. I guess the first one is this representation is hard to use. So whenever we need to work in binary, the problem with it, what makes it hard to use, is those strings become so long because we need so many symbols. Kind of like that ancient Egyptian thing. They actually wrote their numbers in base 10. Price tags at the store were written with base 10 numbers. But then when they needed to do math, they converted that to base 2 into binary, did all the math with a bunch of yes, no questions, and then converted it back to base 10. So it's that long string of how we have to write it that makes it hard to work with. The human mind can handle better than that. So we need another symbol, another base that we can actually work with that works nice for binary. We have some restrictions. It has to relate to binary directly. So whatever number we choose for our base can only be built out of the number 2. When I get back to the board, we'll see what that means. And it has to be a reasonable number for humans, a better number for humans to work with. 2 is not enough. It's too simple for us. That's the problem. The human mind can't simplify itself this far. We can deal with more than just 2 symbols. So as we look for a better base, in order to match binary, it has to be built up from 2s. So 2 to the first power is not going to work. Well, 2 to the first power is not built up of 2s. 2 squared, it's only built up of 2s. 2 times 2, that's 4. It's better than 4 symbols are better than 2, but as humans, we can do much better than that. Right? Normally in America, we deal with 10. So 4 is still kind of small. So if we take 2 squared or 4 and square that, we get 16. That's a better number. It's more than we normally use, but not many more. 10 is based off our fingers. If we use our fingers and our toes, we're past 16. So that's easily in the number of symbols we can handle. If we tried the next one, we squared this again, we get up to 256. That might be a bit many symbols for humans to deal with. It's actually not, but it seems like it when we say 256 symbols. We definitely deal with more than 256 symbols in our lives. If you look at your keyboard, how many symbols are on there? Counting uppercase, lowercase, special characters. And that's not even every symbol we use, because periodically we need symbols for our Word document that aren't on the keyboard. And we have to use like the right alt symbols. Hold the alt key on the right hand side and type in the Unicode value. And that will insert the symbols that didn't make it on our keyboard. So 256 is too big. At least in theory. Technically, humans can handle way more symbols than that. Our brains are very, very vast, but that's a number we're going to start panicking over. So base 16 sounds good. So we need 16 symbols. Base 16 for our symbols. We're still going to tie things back to math. It's a mathematical thing. We need numbers. So obviously the first 10 are the ones we normally use, 0 through 9, but then we need 6 more symbols. So the most reasonable things to use are the first few letters of the alphabet, the symbols we're most used to using. So 0 through 9 and A through F, which does still count on our hands. I'm going to turn the camera back on here, put my hands someplace where people in the room can see it as well. So what I do for counting hexadecimal on my fingers is 1 through 9 is normal, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. But then when you get to 10, start with an empty one. And that is now A. And we can do A, B, C, D, E, F. And we can count 16. And to get used to those, just remember 10 is A, so start with no fingers, and then go through 11, 12, 13, 14, 15. Because 0 is one of our symbols. So 16 symbols is only the numbers 0 through 15. We don't want to leave that one off. So you get used to it, A, B, C, D, E, F. And what that really is, since it's built up of this, we can use it to work in binary directly, but we can work in binary 4 bits at a time. this is too simple, so we need to kind of clutter it up. So I'm gonna make up a number here. Let's say we have 10110110. We have this number and we need to convert it. So we could do what we did here, go through every column and add it up. But a quicker way, and the reason we have this, is to work with, we can work with it 4 bits at a time. Because if we split that in half, in this half, we only have 4 bits. So with these columns, instead of going 1, 2, all the way up to 28, we only have 1, 2, 4, and 8. Those are numbers small enough, most of us can deal with that in our head. Right? We have, those are numbers we don't even need all of our 10 fingers to count on. So we split it up into 4 bits and then do each bit separately. 1, 2, 4, 8. So in this case, do we have any 8s? Yes. 4 is a no. 2 yes, 1 yes. So 8 plus 2 plus 1 is 11. And then again, A is 10, so A, B. That gets up to 11. So this one is a B. 0, 8s, a 4, a 2, and 0 would be 6. That's in our lower symbols. So that one is B6 in hexadecimal. So really it's 4 bits at a time. But now we have a base 16 number. So we only have 2 columns to work with, 16 to the 0 column and 16 to the first column. So we have 11 16s. (11 times 16 plus 6 in the 1 column. 11 times 16 is 160 plus 16, 176. Plus 6 is up 182. So that's what that number would be. And we only have 2 things to deal with instead of 8, like we did here. So that's why we use hexadecimal. And sometimes we do want to work directly in binary. Colors are a big example, because when we want to set a color on a screen, we want to do direct electrical control over the red, green, blue pixels, which means we really want to be working in binary so that we have exact electrical control over those pixels, so it's the same color on every screen. But typing in 100101011, all of that is kind of hard. So if we type it in hex, and then the computer just translates that to binary, and that direct relationship. We're working with it 4 bits at a time. Then we can do conversions. So if we had a number, let's say 203 in base 10. I guess we didn't do many conversions the other way. To get that to base 16, we divide and take the remainder. So like long division, 203, we want to go to base 16. So 16, we'll go to 203. And let's see, 10 times is 160. So we can go more than that. 12, let's see, 12, 14. I'm gonna grab the calculator. We have a machine that does this.
That's 12 times.
Huh?
12 times.
12 times. Or we have technology. There's lots of calculators that'll do remainder division. Oops. 203 remainder divided by 60. Oops, wrong button. 203. There it is. Remainder division by 16, and we get 12 with a remainder of 11. Which, with our symbols, 10, A, B, C, 12 is C, and B is 1, so this would be C with a remainder of B. And then we can take that and do 4 bits at a time. So C is a 12, so we only need 4 bits. So 8 plus 4 is 12, so the next two are 0. And then B, we have an 8. 4 would be too big, so no on the 4s. 2 more gets us to 10. 1 more gets us to 11. So it's a very quick process to get through that, there. But again, technology will do that conversion for us. I think the battery died in the one in my backpack, but the calculator from the Dollar Tree, so $1 calculator. I think I showed you saw this in the previous class. So if you go get the ones at the Dollar Tree, notice above the subtraction symbol is hex, so it'll do hex conversion, and above the division symbol on that is BIN, so it'll do binary. So a $1 calculator will do all of this for us. It's just fairly customary to do it in the class, go over it, and in the 120 class, I usually ask people to do it once, and then talk about the calculators and make sure everybody can use the calculators and conversions. But this is one that will show up a lot for programming, because sometimes we do need to work in direct binary, be there directly on the machine. And when we do that, typing 1 and 0 is hard. So we type hex, and really that's 4 bits at a time. We type binary 4 bits at a time, is what hexadecimal is for. It's in math, just a quick note, you all would have seen it in the previous class or heard it mentioned. When we need to do math like we did here earlier, we had that carry into the next column or borrowing from a column when we subtract. There's a bunch of stuff there. What we really need is one operation we can build all of math from. So instead of having math addition and subtractions defined differently, we need a way that we can add in order to get negative numbers. And there's this old trick, another one of those old tricks called 2's complement. Complement is what we need to add to get to our highest digit. So if we're in base 10, like we know, if we have a 7, we need to add 2 to get to our highest symbol, to get to 9. If we have a 4, we need to add 5 to get to our highest symbol. There's a lot going on there. But it turns out if we take the complement, and we take all those complementary numbers, the one we would add in order to get to the highest symbol, that's the first degree complement. And then our second degree complement, we add 1 more to that. Because if we just took the straight complement again, we get right back where we started from. So like the first degree complement is what we need to add to get to our highest digit. Then we add 1, that's our second degree. We add 2 to get to our third degree complement, add 3, fourth degree complement, and so on. But at the second degree complement, if we add 2 numbers, so let's say this has been up here for a while. This is something called the 0 problem. If we just try to define special symbols and stuff, positive and negative as different things, we end up with 0. So it was a while ago, we'll come up with solutions. So in base 10, if we wanted to do, say, 10 minus 7, what we can do is switch that to addition by taking the complement. So our highest symbol is a 9. So to get from 7 to 9, we need a 2 is the complement, right? So the complement of 7 is a 2. And then we add 1 to get our add 1 to get our 2's complement, our second or the second degree complement. So that would give us a 3. 2 plus 1 gives us a 3. And now we can add. And we get an extra digit. I probably should have done something without the 1 there. But we add and get 1 extra digit. So now 10 plus 3 gives us 13. So if we disregard that extra digit, because it will always give us an extra digit, anytime we do 2's complement, whoops, that gives us 13. We get the same thing as if we would have subtracted the numbers, but really we're only doing 1 operation. And it looks like a mess here, right? So let's try a different one. 10 minus 22. Oh, let me change that up. 26. So we need to complement that, which is what it's going to get really, really simple here in a second. So yeah, this is just for an example to show that it's, since we use the word 2 for the second degree thing, a lot of people think this is solely a binary thing, but it's a number thing overall. So our complement is what it takes to get the highest digit, which would be 9. So 6 is 3 away and 2 is 7 away. So the complement is 7, 3, or I should say all 9s. We take each number and try to turn it into a 9. See what it would take to turn it into a 9 is our complement. Then our 2's complement, we add 1 to that. It's 74. And now to do our subtraction, we can add those numbers. 10 plus, or 0 plus 4 is 0, 4, 1 plus 7 is 8. And from what we fed in, we're probably expecting a 2-digit number. So our extra digit's a 0, which means we have a 2's complement. So if we subtract 1 from that and get 83, and then complement that, 8 is 1 away from a 9, and 3 is 6 away from a 9, we get the same thing from adding. So that's an old math trick. 2's complement is kind of a mess because there's that little jumbled around part of what a complement is. Right? It's what it takes to get to our highest digit. But what is that case when we only have 2 digits? If we're at 1, we add a 0. If we're at 0, we add a 1. So in base 2, that complement part, which was the most complicated part there, is really, really easy. And then we can do all of math from 1 operation by doing using the second degree complement. Because if we complement and then complement again, we just get right back to where we come from. So we complement and then add 1 for the second degree. And then that gives us this useful little trick so that we only need 1 operation to build up all of math from. We get our positive and negative numbers all defined nicely that way. And the part that's hard about it is taking that initial complement, because adding 1 is easy. And when binary makes that initial complement easy, 2's complement gets really, really easy. And the key thing there is a computer only needs 1 circuit to do all the math. Because then all it needs is a circuit that can add things. That can combine 1s and 0s in those columns and carry them if necessary. And then we only need one circuit to do it. So we build a circuit that can do 2's complement with binary numbers, and that's what an arithmetic logic unit is. The actual, the thing that we move our numbers through in order to change them. A whole bunch of number stuff there. But this old math trick, which was complicated, gets easy in binary, and it gives us one operation to do all the math. So that's what's actually happening in the computer. We talked about these integer representations. That's always the way it's introduced. That is not the integers we use when we're writing programs. That is nothing like the integers we use when we're writing a Python program. Give it a try. Save next time you're sitting down to practice some stuff with Python, you're probably going to be anxious to after a bunch of talking this evening. Try putting a variable holding one integer, just something that would fit in like 8 bits. So maybe the number 37, because we know that should be 8 bits of data. Save that and see how big it is. It's not 8 bits in Python. It's going to be closer to a kilobyte. So this is not this is the base foundation of that. We use more complicated things when we actually get there. But just making sure all of these concepts from that you would have seen in the previous course make sense. It's okay if I erase the board. I see a head nod here. So that finishes the number stuff, but not the math stuff. Because as I erase this, math is really about how things change, right? When we add and subtract numbers, there's a change happening. So it throws people off when they first hear it described that way or have to think about it that way. But math isn't about numbers. Math and numbers are separate from each other. And math does not rely on numbers. We can do math with things other than numbers. So we're done with the number part, but not the math part here. And this marker just does not want to erase. Because in the early days of modern math, people were asking that question, like, how dependent on numbers are we? And modern math is really about examining what that dependency actually is. And we're not very dependent on numbers. The math is really the study of how things change. Or either how things change or a description of them. And there's more things we can use. My biggest interest in math, when I study it specifically, it has to do with abstract math and representation, how we represent things. In particular, representation theory, where like plotting things on a graph, you're probably used to plotting things on a graph, like from your math class. You may have some strange looking curve there and make sense of it there, but there's other things we can do. Like my biggest interest has to do with ways that we could change the graph that's plotted on so that the thing we're plotting becomes a straight line, and then our graph, the space where it exists, changes. or different ways to represent it. One of my biggest interest is different ways we can represent things, like we can use little lattice-like grids and represent all of our math using pictures, or knots is one that I'm really interested in. We can represent math based off how things are knotted. The way we tie knots together can represent, the things we think about with math can be represented that way. And take a piece of string and do all of that stuff. So numbers aren't the only thing we have to work with math. And we just talked, well, reviewed. Hopefully that was reviewed for everybody. It was awful quick if that was the first pass at it. Hopefully it was review, triggering some of those bells. So there's other things we can use. Our machine does math. So what else can we do? In the early days of modern math, somebody asked that question, what else can we use? And in particular, he was concerned with truth. Studying philosophy and metaphysics, when can we say things are true? How far can truth be stretched? Those sort of deep philosophical questions. So he was concerned with that. And he sat down and realized that we can do it. Our operations are different, but what causes that interaction? That's what that is, the change, the interaction between things, or the lack of change and lack of interaction. That is, falls in those categories. We can apply the same rules to the study of truth, where we'd have two values. Things are either true or false, and all of our math can be built up that way. But our operations are a little bit different, but they still follow the same order of operations. We just need a couple things to work with it. How do things interact? And there's a very short list. First of those is not. I'll write our operations in all uppercase letters. We could set the negation. If it was true, we'd say not. We can apply the operation of not, and not true gives us our other value, or vice versa. Not false gives us our other value, gives us true. So that's an operation. It stays within the set of values we have. Here's all, think of it as that's all the numbers in the universe. This operation stays within there. It doesn't leave it, so it changes it, but we haven't left that set we have. We also do and. And is like a court of law. The truth in the court of law. The truth, the whole truth, and nothing but the truth. So we can put a whole bunch of different true things together. As long as it's like a court of law, the truth, the whole truth, and nothing but the truth, it's still true. If there's any false in that, we're gonna disregard all of it. So that is not the whole truth. It is not all entirely true. So and the inclusivity. As long as everything is included, that's an operation that stays within our possible set of values. The space of possibility we have for this. We also do or. Things can be either true or false. So it's the opposite of a court of law. That's like grasping at straws. Grasping at straws, you're hoping that what people told you isn't true, but you're pretty sure it's false, but you'll grab any truth you can find. So if there's any truth whatsoever, that truth is what we hang on to. Versus and, if there's any false whatsoever, that false is what we hang on to. And those give us enough to build up a full mathematical system. So we can do a mathematical evaluation of any philosophical statement using these three operations and these two values. Key thing there is two values. It's a binary state. Any way we want to represent a binary state should match that pattern. We have two things and three operations. So any binary state that has two values and three different ways we can approach them should follow the same rules as that sort of Boolean logic was the name for it. But it gives us ways to combine things. And since computers are binary machines, these operations still apply. And in particular, we can extend it a little bit further into the math we're normally thinking about and use true and false statements. We'll see some extensions of this when we get to code and things that go that would be a mess to write on the board. But our basic math operations, these things can be applied to. First off is equality, which since we're in programming class, I'm going to write two equal signs. Usually equal signs, one equal sign is our assignment operator. I think everybody's seen that before. So two equal signs means equal to. We might also see three equal signs that is strictly equal to. For example, true and false, we typically would represent those as ones and zeros. So true is equal to 1. True is equal to 1, but true with three equal signs is strictly equal. True, that's not, true is not strictly equal to 1. I should write that in red. Because even though they're interchangeable, it's just different symbols for the same thing. That makes them equal, but they are different types. This one we're thinking of as like a true false value, and this one we're thinking of as the number 1, as in 1 and 0. So they're not strictly equal. They have a different type to them. I'm just going to do the two equal signs for this stuff tonight, though. But keep in mind there is three equal signs as well if we need to worry about the type, because our values would be okay otherwise. Or another example, 65 is equivalent to a capital A. They're equal. In ASCII code and Unicode, a capital A is the number 65. But they are not strictly equal because this one's a character and this one's a number. So that's where the three equal signs come in, and then some of our other ones less than or equal, greater than or equal. Same things without the equality to it. And these give us truth values, right? Two numbers are equal. It's either a yes or no question. It's true or false. If we write that down, it's either true or false. So we can check that, and then we can combine them with our logical operators, which would have showed up in the previous class. Oh, and then we can combine our operations as well. I guess I should talk about order operations. So in your math classes, you probably remember that there's a certain order we perform all our operations in, right? Everybody remember that from math class? Does anybody remember the operations we perform, or the order we perform our operations in? I see a head checking no in the classroom, so I'll write it up here. Do you remember seeing this in your math class? we'll do parentheses, so anything that groups our numbers together. Then exponents, then multiply, divide, and add and subtract. It's kind of like a staircase. When we have a big math problem to solve, anything that groups our numbers together, we have to do that first, do all of those, and then we go up to the next step. And then we can do any exponents. And after we do all of the exponents, then we'll do multiplication and division, because multiplication and division are actually the same thing. We just learned it as two different things.
Is it the same thing as Podmers?
Hmm?
Is it the same thing as Podmers?
I couldn't hear the last word.
Podmers.
Oh, the module,
Podmers, like Podmers, BOMASA.
yes, I think it would just say. So you probably learned some different ones, but I was going to generalize it. Usually we hear this. So parentheses, exponents.
Same Podmers is bracket something.
Yeah, brackets. Then yeah, I was going to talk about that because this is the way we learned in America, which is a little bit off. And then add and subtract are really the same operation because we have negative numbers. So adding a negative number is the same as subtracting. Hopefully this is all stuff you've heard before. So our logical operations kind of follow the same suit, except that it's a couple of these labels are wrong. The parentheses is really anything that groups our numbers together. So parentheses, a fraction bar, like square root symbol, all the stuff under that square root symbol gets done before the stuff outside of it. Anything that groups our numbers together. And then exponents, people learn that young. What it really is our unitary operations. Yeah, message in the chat room, that might be a problem, what was causing the problems in the program, which means you might need to put some parentheses, some extra parentheses in there. But exponents, we learned those because we have that in our word because E gives us a vowel and makes that like we can pronounce it, and there's E is the second most common letter used in English. So when we make an acronym out of it, when we make a word out of it, by the way, not an acronym, anagram. When we try to make a sentence out of it that's funny or inappropriate, not the one you heard in math class, probably please excuse my dear Aunt Sally, but if you check Google for things, order operations, ways to remember that, you'll see lots of funny and inappropriate ones that have no place in math, no place in the classroom, but are a much, much, much better way for a human to remember it. We're humans, we'll remember the funny and inappropriate things, especially inappropriately funny things that have no business in the classroom. We will remember those a lot better than the nice formal stuff. But what exponents really is it's our single operation. It's only take one number. For example, squaring. 2 squared, it looks like it has 2 numbers, but this little 2 up here is the operation. Right? It's not a 2 per se. That's the operation we're performing. So really, we need one number in order to square it. We need to know which number is being squared, and so it's our unitary operations.
I think it's the same thing as the Podmers I'm talking about. Bracket, order, division, multiplication, addition, and subtraction.
Yes, there's lots of ways we can do it. So really it's anything that groups our numbers together, all the unitary operations, and then all the binary operations, but they go in order because we have different levels of binary operations. Some of them are closer together than others. Multiplication and division are closer together than addition and subtraction. What's a good way to say this without getting into high level math? To multiply and have the same and keep the same number, we multiply by 1, right? And to add and keep the same number, we would add 0. So it has to do with that. But I'm going to drift into high level math if I think about it. Multiplication is more inclusive. Well, we multiply by 1, which is a number, and there's a number we can multiply by and still have the same number. So it's inclusive. But for addition, we add 0 in order to stay the same. And 0 is a very special number, right? So it's like almost like it's further apart or not as inclusive. There's a whole bunch of things here, but that's going to get complicated. Multiplication, think of multiplication as closer than addition and subtraction. And I can't think of any good ways to put it there. But inclusive. Multiplication is lots of additions. Okay, so we combined lots of addition together to get multiply. So they're included. That might be a good way to think about it. So inclusivity. So lots of addition together. It's almost like a grouping thing again. We regrouped some of our addition to make multiplication. So we do that first. Inclusivity first. Inclusion first. And I was looking for that word, inclusion, inclusivity, something like that, because it relates here. So grouping would still be grouping. We wrap things in parentheses, or we need to keep it nice and neat on paper. And in some programming languages, we can use brackets and curly braces to help keep track of which one's which. And that way we don't end up with 20 parentheses that we have to make sure every set of parentheses is closed later. In most of our programming languages, we have to do that because brackets and curly braces mean something different. But whatever groups our logic together. 2 is less than or equal to 7, and 99 is less than 1 million. We can combine those with an and still have truth. 2 is equal to 7, or 99 is less than 1 million. One of them's false, but one of them was true. So with or, we'll hold to that truth part, and we would still count that as true. So the ways we can combine them. So the and is more inclusive. Our inclusion one goes first, and not only happens to one thing at a time. So not true or not false. Not true and true. We'd have to combine those truths into a single true before we can apply the not to. So not is a unitary operation. And an or are binary operations. They take 2 things. We can't say this or and then just stop, right? That's a whole famous saying. This or that. We need the 2 things. So the binary operation and is inclusive, because or doesn't necessarily have to be. So and goes first. And or. I'll just write parentheses again here. So parentheses first, just like we're used to. But it's the same order of operations we know from math. Do the parentheses first, then any negations. Then we do all of our ands going left to right. And then we do all of our ors going left to right. Because just like multiplication and division and addition and subtraction, Sometimes it does not matter, and sometimes it does matter. So instead of having to stop and try to figure out whether it's a time that matters or not, we just always go left or right. That way we don't have to worry about whether it matters or not. We just act like they all matter, and then it always works out the same. So same thing with and or. Actually, electrical engineers actually write multiplication and addition for and or. So it's even closer if you want to use those symbols. That's electrical engineering. Multiply the ands and add the ors. You might have also heard that some people hear it when they're first learning math in elementary school. And I remember sitting in 300 and 400 level classes and people being surprised because they'd never heard that before. I heard it in elementary school, but it's consistent from the math I've seen. I can currently say from kindergarten up to 600 level math classes, multiply ands and add ors. The way we use those words translates directly over. Same thing with logic. So we have a machine that can do this, all this stuff, and handle this for us. Let's review here. So the ordered combinations we do these things is the how of the process. So that's the mathematics, the how, the arithmetic logic unit. Oh, and this happens in the arithmetic logic unit as well, because to compare things, all we do is subtract. If we subtract two numbers, we want to compare two, and I should avoid two. We want to compare two numbers. So let's say 3 and 5. If we take 3 minus 5, we get a negative number, right? That's how we would determine this. So we just subtract the numbers. This number, I'll write X's and Y's here. X's and Y's. So if we take whatever number is in this variable X minus the variable Y, if we subtract them and get a 0, that means they're equal. We only get a 0 if they're the same number. If we subtract them and get a positive number, X minus Y, and the result is positive, is X greater or?
That means X is greater.
Yeah. And if we subtract them and get a negative number, that means X is less than. So add and subtraction gives us that comparison. So all of that, that's what the machine is actually doing. Machines don't do complicated things. It just seems like it when you don't know the whole picture and see a whole bunch of ones and zeros there, it's like, that doesn't make any sense. How does a machine work with that? With what they mean, we can do math with them and we can subtract them. So we can do our regular math like we know, and then we can subtract them for our comparisons and add in our Boolean math and get back to true and false values, and it extends we can extend it from there. But that's the how. So real quick on the where, because this is not an IT so this is an IT support class, but we need to think about these other parts. Oh, I forgot to ask if I could erase that. I think it's been up there for a minute, hasn't it? Sorry, I've been talking since 1 o'clock this afternoon. Yeah, and at least a couple of people on the Zoom call have been listening to me since we'll talk since 1 o'clock this afternoon, except for a very short break. My throat's going to be sore this weekend, but hopefully I'll be used to it by next week. Actually, tonight's the long day in both classes. Tonight's probably going to be the longest. Today's going to be the longest day because we got to get through all this review stuff tonight. And then this afternoon, I wanted to get all the fundamental pieces of making a game before the first weekend. And now we can just make improvements on those fundamental pieces the rest of the semester. So today's a long day, but how does the machine work? we know we're gonna get some sort of input. And that input is going to flow into a CPU. We know there's a CPU there, we know something's happening. Connected to that CPU, we might have some ROM and some RAM. And somewhere off to the side, we have long-term storage. The random access memory can get the stuff stored for long-term, for temporary storage. Our volatile storage, so input goes over to processing, storage if we need it, and then eventually to our output. That's the general flow of that, and those shapes I drew there are not arbitrary. We live in a global world. It's a global world. Politicians want to deny it. They still want to draw their borders there because they lose the power if they erase their borders. But that's an outdated system. Computers are very, very quickly made one world, not a bunch of separate countries. It's just the politicians are refusing to let go. But they're not going to be able to hold that up indefinitely. Technology has already surpassed them. But we speak lots of different languages around the world, right? For example, if you get when you graduate a software developer, go get a job, make it Google, there's a good chance you'll be on the team of developers. And some of the people on that team will be in San Francisco. Some of the people on that team will be in Hamburg, Germany. Some people on that team will be in just some cities on the south side of Beijing, suburbs on the south side of Beijing. And some people on that team will be in Accra. Is it Accra or Agra? Capital of Ghana.
Accra.
Accra. And some people will be in Accra. That is the most likely place that your teammates on a Google development team will be at. There's a bunch of different languages spoken there, right? That might not be the best example because every one of those people in Accra every one of those people would know English, even if it's not one of their official languages. But we can say they speak different languages, and we need a way to communicate with that team. So there is an international standard of communication, a language that we communicate with. It's called Unified Modeling Language, and it's a pictorial-based language. So it's an international standard language that everybody in the entire world uses, and it's pictorial-based. So we just need, so people in China, and Germany, and Ghana, and California, those places I just mentioned where your teammates on a Google development team would most likely be from, their students in those countries learning these same symbols. They have an instructor saying, okay, these symbols I just drew on the board are not arbitrary choices. It's an international standard of communication. And some fields of IT do a lot more international communication than others. Software developers being one of those, because unlike people plugging up a network and running cables where you need one person pushing wires into this wall and somebody in the next room over pulling them down and somebody in the attic going across, that's fine if they all speak the same language. But software developers, there's no need for us to be in the same room with our teammates. We can be anywhere in the world. So software developers definitely do a lot more international communication. So Unified Modeling Language, or UML, is one of the things we're going to look at quite a bit in this course as well. Get used to what all those pictures mean. This is storage. It's supposed to look like a stack of disk. I've heard it said most often like a stack of the old reel tape things. But UML was created in the 1990s, and that reel-to-reel tape data storage was way outdated by then. So maybe a stack of hard disks or something. A stack of cylinders is the symbol for long-term storage. Whatever it's supposed to represent. Square boxes are for volatile storage. Parallelograms are input and output, and we will see lots and lots of those symbols throughout the semester as we go along, because that's one of them important for software developers. There's a couple pieces of it on a CPU. Let me draw the CPU picture. Let's expand the CPU out. And real quick, the core pieces we need to run a CPU. We need a control unit. And I mentioned the arithmetic logic unit. That's the thing that does the math. We also have a floating point unit, which is exactly like the arithmetic logic unit, only everything's reversed. Because in our columns, we only did integers tonight. I think the powers of 2 grow as we move right to left, just like our numbers. But when we get fractional numbers, it grows the other way. The power of 2 is on the bottom of our fraction, but 2 to the first is our is the one all the way over by the decimal point, and then 2 squared is the next one, 2/3. So the integers and fractional numbers go the opposite direction. So there's 2 of those pieces, one of them to handle the whole number side and one of them to handle the fraction number sides. They're exactly the same, only like mirror images of each other, so they go the other way. In the arithmetic logic unit, the carry bit goes that way, and in the floating point unit, the carry bit goes that way. Is the difference between them. We need a clock to synchronize everything. A synchronization clock. So it's not a steady beat like a timer clock, the clock on the wall, the clocks in Paris that all of our machines tie to, the steady pulse to track things. This is a synchronization clock, so that after we run the next instruction, we're ready to do the next instruction, the clock ticks. And then we run the next instruction no matter how long it takes. When we're ready for the next instruction, is a tick of that clock so that everything synchronizes together. So it's not a steady beat, steady pace, but we still call it a clock because it's what synchronizes it. Like the clock on the wall tonight at 6 o'clock is how y'all knew when it was time to come to class. It's the clock. A clock is what synchronizes everything we do together. I'm going to write RAM kind of overlapping. RAM is a separate piece. Anybody that's ever opened up a computer probably knows that. You can pull out your RAM chip without touching the CPU, or swap out your CPU without touching your RAM. But we could not use a CPU without RAM. And RAM couldn't do anything without a CPU. So they're not independent pieces. We can't do anything with one of them without the other one. And then there's some registers. So registers are like RAM. It's volatile storage, temporary storage. RAM holds the current program we're working on, and registers hold the current step of the program. Does that make sense? We're going to write text files all semester, so think about it in the lines. RAM holds all of those lines of code we write, and the registers hold them one at a time as that instruction is being carried out. So RAM holds the whole program, and registers are one instruction, holds the current instruction. Current program, current instruction. That's the main pieces. And then there's a flow from it. So really our input I'll draw another little picture here. So we get some sort of input, and then that gets pushed onto RAM. And I am making up the words push and pull to help visualize what's going on here. I'm gonna say push and pull. And by push, input pushes RAM. By that I mean like the keyboard has mechanical components. So when I push a key, the input device has all the stuff that changes. And RAM just catches whatever's thrown its way. But RAM's just standing there with its hands held out. So when a key pushes, RAM's gonna catch that electrical signal when it starts flowing. So I'm gonna use the words push and pull. Those are not technical terms. That's just how I think about this flow. From RAM, that gets pulled onto our control unit. And by pull, I mean the control unit is the active one. RAM's like a bucket. RAM's just standing a bucket, or I keep trying to anthropomorphize it. RAM's standing there holding a bucket, and input puts stuff in that bucket. The control unit can pull stuff out of that bucket, but RAM can't do anything with it except stand there and hold it. That's what I'm using push and pull from. Those are not technical terms, hopefully to help visualize what's going on here. The control unit, which is an active piece, then moves on to some passive pieces. It will push things onto the ALU or the FPU, whichever one it needs. Yeah, push. And the registers pull things from there. So that's another difference between RAM and registers, is the active versus passive pieces. The registers can do stuff with what they're holding. They're a bucket just like RAM, but maybe you can think of it like a bucket full of springs. So when you throw something in that bucket, stuff bounces out. Active and passive pieces, that's what I'm using push and pull for here. And if that's the final result, the registers can then push it to the output, which is another passive piece. Output can only do what is pushed onto it. It's a bucket, it holds stuff. If that's not the final output, it can also come back around. Whoops. These haven't been erasing, so a dash line doesn't work very well. It can also push it back onto the ALU or FPU and keep looping through those until it does get to the final output with a signal back to that. So active and passive, some pieces are active, some pieces are passive. It's a continuously running cycle of, so the clock continuously running, cycling from input to output, maybe looping around inside there of what the control unit is doing. And what the control unit does is the same cycle over and over and over again. And that is fetch, increment, execute. So really, this is what the CPU does. That marker's not done for. I think that's all my black markers. There you get some more black markers. Blue still looks okay. So the control unit, and oftentimes we say this about the CPU itself, because the control unit is the most active piece there. It's not the inputs active, control unit and registers are active pieces, and RAM, the arithmetic logic unit, and output are passive units. So like the arithmetic logic unit, all we have to do is when we send that electricity there, it doesn't do anything with it. It just follows a pattern and handles its processing, which is well, really added together. So the control unit constantly follows this repeated cycle: fetch, increment, execute. What that is it's going to fetch the next instruction from RAM. Increment is what I've left in this picture over here. I noticed there's a big corner on that picture I didn't fill in yet because it wasn't in the middle picture. We also need a counter to tell what instruction we're on. Right? When our program's in RAM, so we want to run instruction 1, then instruction 2, and instruction 3, and they need to go in a certain sequence. That very first thing we started off with tonight, the sequential tool, the order manners. So we need to increment our counter and then execute our instruction. Execute instruction. So fetch the next instruction, grab it from RAM, pull it from RAM, push it onto the ALU or FPU. But there's an increment in between. You see why the order matters here. What would happen if that switched? Would it be okay to fetch the instruction, execute that instruction, and then increment our counter? Does anybody see a problem with that?
No, it should be fetch, execute, and increment.
Oh, it goes this way. Because what if the instruction is jump to number 19? So we grab instruction, maybe instruction 12 is jump to instruction 19. We grab instruction 12, increment our counter, it's at 13 now. Then execute says jump to instruction 19. So our counter, that changes our counter. But if increment came last, we would grab instruction 12, jump to instruction 19, and then increment our counter would put us on 20. But we should be on 19. So that's why we want to increment first, because our instruction could be to change the counter. Our instruction could be to go to another instruction, like in a loop or selection structure. That's how we do selection structure. Jump to this other spot instead of running everything. Well, if we're on 12, jump to 19 and do that stuff. That's like the else block. You can think of that like the else block in an if else. Or a loop. We get down to instruction 19, and instruction 19 is go back to instruction 12. And that keeps us going around in a circle. So that's the where part. That went a lot quicker than the how, right? How was like a whole bunch of stuff, the math and stuff, and then the how part was all the math earlier. Here's the where part. It's happening in the CPU, mostly in RAM, some in storage, but just in storage when we need to keep things around. So as software developers, we are mostly in this piece right here. We're working almost entirely in RAM. Is where we're going to be focused on in this class. That's our where. And the why part is what the whole rest of this class is about. So that finishes our review. And the whole rest of the semester will be covering concepts through examples. We'll write some Python. We'll talk about something, then write some Python code, then talk about that code we just wrote, what it does in the background. We might even convert it to assembly language to see what it's doing to the machine. But the whole rest of the class will be example based. We'll talk about it, write some code, talk about it, write some code, and we'll see it in action because that is the why we do this. We saw how we process, where we process, and as software developers, the part that really concerns us, and the reason this was all turned into one night to get out of the way, is why do we run things through a process? Why do we want to process that? And the answer is what we started off with tonight. The problem, solve problems. That was a whole bunch of stuff, but hopefully it was review and things that you may have heard along the way, just because computers have, our world is fully dependent on computers. We've, very, really bad things would happen if we suddenly lost all our computers. But there's enough people that know how to do this. It's not going away. It's gonna take, it'll be a couple generations. One of my favorite things to say, people worry about using a calculator. It's like, we have a tool that does it, that does our math, and it's, if we were suddenly without calculator, we won't have to worry about a lack of a calculator again, until the only thing we have to worry about is getting the harvest in and fighting off marauders. When society is eventually completely collapsed and we're the complete dystopian future where we're barely a couple steps above wild nature again. That'll be the next time we have to worry about not having a calculator. The knowledge is widespread. There are a whole lot of us that can build this from scratch. The knowledge isn't going away. So these tools are around to stay. Very useful thing. That was a lot of talking tonight. That was definitely the most talking we will do. It took our entire class period. We will not have another class that goes all the way to the end. But I wanted to get all that out of the way, so now we can do the fun part. On Monday, when we get in class, we can jump right into the fun part, which is writing code, and not have to worry about all this stuff. But I have been talking since 1 o'clock. I'm ready for a great big cup of coffee that's so hot it almost burns my throat. Hopefully relaxes that a little. Does anybody have any questions? Give it a few seconds. Okay, I assume 5 seconds of silence means no questions. Y'all have a great weekend. If you have any questions, send them to me. I'm always happy to help. I don't have much of a life outside of this, but I am teaching a bunch of classes this semester. But I will address questions as quickly as possible. I learn messages and text messages are the two things that make noise on my phone, so that is the quickest way to get a hold of me. If anybody's willing to try VR office hours, I want to give it a try so I can figure out what the problems are that need to be addressed, because that's seems like a useful way to do that. If anybody's willing to give it a try, let me know. We'll set up a time. Otherwise, I assume silence means from the Zoom call means no questions. So have a great weekend. I will see you on Monday. And the review is out of the way. We jump right into the fun part on Monday.
All right, you have a good weekend.